Hello friend, welcome to the static algebra class. In this class we will prove this theorem. It is class 12. A finite, the theorem, the statement of theorem is a finite semigroup with respect to multiplication satisfying consolation laws is a group. We now prove this theorem. Let G equal to A1, comma, A2, comma, A3, comma, and so on, AN be a finite set with in distinct element with indistinct element suppose G with respect to multiplication is a semigroup satisfying semigroup and satisfying consolation laws, then we have to prove that G with respect to multiplication is a group. Again, we see the statement, a finite semigroup with G with respect to multiplication satisfying consolation laws is a group. Group let G is semigroup. We suppose that G is a finite group. A1, A2, A3, AN, and so on. AN is the element of G. Be a finite set with indistinct elements. Suppose G with respect to multiplication is a semigroup and satisfying consolation laws. Then in the previous classes we studied consolation laws. Then we have to prove that G with respect to multiplication is the group here. G with respect to multiplication is a group. Let A belongs to G. Consider the product A1, comma, A2, comma, and so on, AN. A belongs to G. A1, A2, AN also belongs to G. Then consider the product of AA1, AA2, AAN. Since G with respect to multiplication is a semigroup, therefore by closer axiom the axiom the all the product. Therefore, by closure axiom in J, all the product AA1, AA2, and so on, AAN must be belongs to G. Well, if possible, assume that A into AI equal to A into AJ, or I is not equal to J, implies AI equal to AJ, which is a contradiction. Therefore, AI is not equal to AJ. For all AI, for I is not equal to the product A into A1, A into A2, and so on, and A into AN coincide with A1, A2, AN in some order. That is for some B belongs to G. This is the equation AX equal to B has unique solution. Similarly, if we form product of an A, A2, A, and so on, A, N, A, we get the equation y A equal to B has a unique solution. Therefore, G with respect to multiplication, semi-group have unique solution. Therefore, G with respect to multiplication is a group. Hence proved. Order of an element of a group. Next definition, order of an element of a group. Let G with respect to multiplication be a group then the order of element A belongs to G. A belongs to G is denoted by OA or modulo A, and defined as the least positive integers, n such that a to the power n equal to e, where e is an identity element and if there is no positive integer n such that a into the power n a into to the power n equal to e, then we say that the order of element A is 0. That is OA equal to modulo A equal to 0 or infinite. G with respect to multiplication be a group. This with respect to multiplication be a group. Then the order of element A belongs to G. A is an element belongs to G is denoted by OA or modulo A, defined as the least positive integer. The least positive integer is inside that a to the power n equal to e. E is an identity element in G. If there is no positive integer, if there is no such kind of positive integer inside that a to the power n equal to e, then we say that the order element of A is 0. That is OA equal to modulo A equal to 0 or infinite. Example: G equal to 1 minus 1 I minus I is a finite set. In G with respect to multiplication is an finite abelian group. Here we know that here the identity element E equal to 1. E equal to 1 is the identity element. 1 to the power 1 equal to 1. 1 to the power 2 equal to 1. 1 to the power 3 equal to 1, and so on. The least positive integer is 1. Therefore, order of 1 equal to 1. Also, 1 next element minus 1. minus 1 to the power 1 equal to minus 1. Minus 1 to the power 2 equal to 1. Minus 1 to the power 3 equal to minus 1. Minus 1 to the power 4 equal to 1. Minus 1 to the power 5 equal to minus 1. Minus 1 to the power 6 equal to 1, and so on. Here minus 1 to the power 1 equal to minus 1. It is not belongs to our definition. Also, it is not belongs to our definition. Here is also it is not belongs to our definition. So minus 1 to the power even integer. All are even integer. The smallest positive integer here is 2. Therefore, order of minus 1 equal to 2. Similarly, I to the power 1 equal to I to the power 2 equal to minus 1, I to the power 3 equal to minus I to the power 4 equal to 1, I to the power 5 equal to I to the power 6 equal to minus 1, I to the power 7 equal to minus I to the power 8 equal to 1. Here they cannot be order because they are not equal to 1. Just remaining I to the power 4, I to the power 8. Here is the least positive integer. O I equal to 4. Order of I equal to 4. Also, now we verify minus I. Minus I to the power 1 equal to minus I. Minus I to the power 2 equal to minus 1. Minus 8 equal to I. Minus 1 minus I to the power 4 equal to 1, and so on. The least positive integers, which it is equal to 1, it is the minus I to the power 4 equal to 1. 1 is the element, the identity element. Therefore, order of minus I equal to 4. Consider order of G. Order of G 1, 2, 3, 4. The number of elements, distinct element in G equal to 4. It is equal to the order of an element. Such kind of group which order of group is equal to the order of an element, they call cyclic group, which we will study in the next in the future. Conclude that order of an element is greater than or equal to order of